everyone, this is lecture 2 on boundary value problems. In this lecture, I will discuss the solution technique for solving a one-dimensional wave equation. Consider an elastic string AB of length capital L as given in figure 1. The string is fixed at the endpoints A and B. This is an elastic string, so we stretch this elastic string and then release it. As we release it, there are vibrations. So we want to find out the types of vibrations for this elastic string. Now the vibrations depend on two important things. First, what is the initial deflection in the string? It means when we are releasing the string, then what is the position of the string? We can have different deflections, for example figure 2, 3 and figure 4, or you can have any other option also. And when we are releasing it, what is the starting speed of the string at every point? It may be different. So this is the problem, an elastic string in a one dimension. We will find out the solution of this problem. So let's write down all the conditions in mathematical form. Equation 1 is the mathematical form of a one-dimensional wave equation. This we get when we model the vibrations in an elastic string. It is given by second order derivative of u with respect to t on left side. This is equal to c square second order derivative of u with respect to x, where this c square is given by capital T upon rho, where this T is the tension in the string, rho is the mass of the undeflected string per unit length. This u is a function of x and t, and this denotes the deflection in the string. So we want to find out this function u, that is the deflection in the string at point x at any time t. Now to solve this one-dimensional wave equation, we have following boundary conditions and initial conditions. Here we are assuming that the string is fixed at the endpoints, that is at x equal to 0 and x equal to L. As the string is fixed, so the deflection is always 0. So we have equation number 2, that u at x equal to 0, but you can have any time t, this is always 0. Equation number 2a, at the second endpoint, that is x equal to L, again deflection is 0, so we have second equation, that is 2b. 2a and 2b, these conditions hold for all values of t. Whatever is the time t, string is always fixed at the endpoints. Now initial conditions, that is the conditions defined at time t equal to 0. The deflection in the string depends on what is the starting position of the string and the starting velocity of the string. So we have two initial conditions. First, initial deflection given by equation number 3a, that at time t equal to 0 at point x, the deflection u is given by f of x. Second is initial velocity, that is going to be the derivative of u with respect to t, and we want this at time t equal to 0, so this is going to be just function of x, so this is gx. So we have equation number 3a and 3b, where f of x is the initial deflection, and very important here that f of x at the endpoints x equal to 0 and x equal to L, this function f is 0 because string is fixed at the endpoints and there is no deflection. Gx is the initial velocity of the string at point x, so as you change the point, the velocity may change or it may be constant. So we have finally boundary conditions given by equation 2 and initial conditions given by equation number 3. The solution of partial differential equation 1, that is one-dimensional wave equation satisfying boundary conditions given by 2 and initial conditions given by 3, is obtained by the method of separating variables. There are mainly 3 steps. In step 1, the one-dimensional wave equation is converted into 2 ordinary differential equations, and for this we use the method of separating variables. In this, we write the function u xt as a product of 2 functions, capital F, which is function of only x, and g, capital G, which is function of only time. In step 2, we find out a solution of these 2 ordinary differential equations satisfying the boundary conditions. And the last step 3, we use Fourier series and we find the solution which we get at this step 2 such that the initial conditions are satisfied, and finally we get the solution of a one-dimensional wave equation. So we are starting step 1. We rewrite a one-dimensional wave equation as 2 ordinary differential equations. So start with equation number 4 and let's assume that uxt, that is the deflection in the string, can be written as a product of 2 functions, capital F of x and capital G of t. Now we use equation number 4 and find out all the required derivatives appearing in a one-dimensional wave equation. So differentiate equation number 4 with respect to x twice. We get second order derivative of u with respect to x is given by f double dash g, that is equation number 5, where this prime denotes derivative with respect to x. Now again start with equation number 4, differentiate it with respect to time t twice and find out the derivative of u with respect to t, that is second order derivative. We get equation number 6. Here this g double dots denote derivative with respect to time. So finally using 4 we have equation number 5 and 6 derivatives of u with respect to x and t. Now use equation number 5 and equation number 6 in equation number 1, that is a one-dimensional wave equation. Substitute the values, we get f times g double dot. This is equal to c square f double dash g. Now separate the terms having time as one variable and x as the other variable. So we have equation number 7. On left we have g double dash divided by c square g. This is equal to f prime second order derivative divided by f. Now the variables are separated, left hand side depending only on the time and right hand side only on the variable x. Now if we see equation number 7, one is function of t only and other one is function of only x, and left side is equal to right hand side for all values of x and t. Hence both sides must be constant, because if they were variable then changing t or x would affect only one side, leaving the other side unaltered. Thus from equation number 7 we can say that g double dash divided by c square g, this is equal to f double prime divided by f, this is equal to constant. Where k is an arbitrary constant, we call this one as separation constant. Here with variable time and x, g and f, they are changing, but these ratios are such that left ratio of equation number 7 as well as the ratio on the right hand side containing variable x, this ratio is also constant. So from this equation we have two ordinary differential equations as f double prime minus k times f equal to 0, that is equation number 8 containing only variable x, and second equation as equation number 9, g double dot minus k times c square g equal to 0. Equation number 9 has only one variable, which is time t. Now step 2, solution of partial differential equation 1 satisfying the boundary conditions 2. For this one, we just find out the boundary conditions in terms of these new functions capital F, which is function of only x, and g on t, so that u equal to f into g, it satisfies the boundary conditions. So I'm rewriting the boundary conditions given by 2, that is u 0 comma t is 0 for all values of t. This is equation number 2a. Then second equation 2b, u l comma t, this is equal to 0 for all values of t. Now use equation number 4, that u is product of two functions f into g, both capital. So equation 2a implies that f of 0 into g of t, this is equal to 0 for all values of t. Now if the product of two numbers is 0, this implies that f of 0 is 0 or g of t is 0 for all values of t. I'm writing these as star 1 and star 2. We will further simplify these two conditions. Now come to equation number 2b, u of l comma t is 0. This implies f of capital F of L into g of t is 0 for all values of t. Now this implies again either f of L is 0 or capital G of t is 0 for all values of t. So we have now four conditions, star 1, star 2, and second boundary condition is star 3 and star 4. Now we simplify these conditions further. Now if we say that star 2 condition, that is g of t is 0 for all values of t, if this is the condition, then according to the formula ux comma t, which is f of x into g of t, this is equal to 0 for all values of t, because we are assuming that g of t is 0. So finally our deflection u, this is identically 0 for all values of t and for every value of x. This implies that there is no deflection in the string. So case is simplified. So this case is of no interest if we take that g of t equal to 0 for all values of t, that is condition star 2. So it's important to just scan the first case star 1, that is f of 0 equal to 0. So I'm rewriting this one as equation 10a. Now going to the second condition, that is 2b, we got star 3 condition and star 4. Star 4 is again the same, that g of t is 0 for all values of t, and if this function capital G is 0, this implies that the deflection u is 0 as discussed in this first case. And again this case is simple. So finally the case is interesting only if we take the first condition, that is star 3, that capital F at x equal to L is 0. So finally the boundary conditions on u, now we have these conditions in terms of function f we are denoting this by equation number 10, that f of 0 is 0 and capital F of L is again 0. After simplifying the boundary conditions in terms of function capital F, now we can find out a solution of equation number 8, which is f double prime minus k times f, this is equal to 0. Now here this constant k is an arbitrary constant, so it can be positive, negative or 0. So we explore all the three values. So I'm starting with the first option, that if k is 0, then equation 8 reduces to second order derivative of f with respect to x, this is equal to 0. We can simplify this and its general solution is obtained by integrating it twice, and the solution is given by equation number 11. So we have capital F of x is equal to ax plus b. Now we find out the values of a and b using the boundary conditions given by equation number 10. Now the boundary conditions are f of 0 is 0 and f of L is also 0. So start with the first condition, that f of 0 is 0. In equation number 11, put x equal to 0, we get a times 0 plus b, this is equal to b and it is 0. So this implies that b is 0. Put it in equation number 11, we have that capital F of x is equal to ax. Now we use the secondary boundary condition, that capital F of L is 0. Put the value, we get a times L is 0. Now there are two options, either a is 0 or capital L is 0. L is the length of the string, so it can't be 0. So this implies that a equal to 0. So using boundary conditions, we have value of a and b and both are equal to 0. As a and b both are 0, so from equation number 11, capital F of x is 0 for all values of x. Now we use equation number 4, that u, deflection in the string, is product of capital F of x and capital G of t. Now here f of x is 0 for all values of x. Whatever is this function g, something finite, f of x is always 0. So the product of these two functions is always 0 for all values of x and t. So this implies that there is no deflection in the string, so this case is of no interest. So now we move to the case 2 and explore other values of k. Case 2, if k is positive number. So let us assume that k is mu square, where mu is not a 0 number. Anything positive or negative but not 0. Now put k equal to mu square in equation number 8. We have second equation on this page, f double prime minus k times f equal to 0. This is our equation number 8. Now put k equal to mu square. Now we can rewrite this differential equation as d2 minus mu square f, this is equal to 0, where this capital D is the simple derivative with respect to x. Now we apply the technique of ordinary differential equations, write down the auxiliary equation corresponding to this ordinary differential equation. This is m square minus mu square equal to 0, m is plus minus mu. So the roots of the auxiliary equation are real and distinct. So the solution of this equation number 8 for case 2 is given by equation number 12, and this is f of x equal to a times e raised to power mu x plus capital B times e raised to power minus mu x, where this capital A and B are arbitrary constants, and we find out values of these two constants using the boundary conditions given by equation number 10. Now the first boundary condition is f of 0 is 0. So this implies that a plus b equal to 0. I am just putting x equal to 0 in equation number 12. So we get a plus b equal to 0, or we can say that b equal to minus a. Now we will use the second boundary condition, that capital F at the point x equal to L is again 0. So go to equation number 12, put x equal to capital L. We get the last equation on this slide, and I am using here that b is equal to minus a. So from here we can take a common, and we have the last expression, that a times e raised to power mu L minus e raised to power minus mu L, this is equal to 0. Now this expression, that is a times e raised to power mu L minus e raised to power minus mu L equal to 0. Product of two numbers is 0. It means either a is 0, or this expression e raised to power mu L minus e raised to power minus mu L equal to 0. Now this expression in the bracket exponential terms, it can't be 0 until unless mu is 0. But we know that mu is not 0. So this implies that a equal to 0. And from the first boundary condition we got the result that b is equal to minus a. So this implies that b is also 0. Now we have a is 0, capital B is also 0. So from equation number 12, capital F of x is 0 for all values of x. And now, as discussed in case number 1, when k is 0, we have in this case also that the deflection u is identically 0 for all values of x and t. So this case is again of no interest. Here capital G, we are not solving that equation, because whatever function g is, capital F is always 0. So the product of capital F and capital G is 0 for all values of x and t. Consider case number 3, when k is a negative number. So let k be minus p square, where p is not a 0. So we can rewrite equation number 8 as f double prime plus p square f equal to 0, equation in the box. Now we solve this ordinary differential equation. The auxiliary equation corresponding to equation number 8 is d square plus p square equal to 0. So its roots are plus minus iota p. Roots are complex and in the form of conjugate pair. So the general solution of equation number 8 is given by equation number 13, which is capital F is equal to a times cos px plus b times sin px, where a and p are arbitrary constants. Now we use boundary conditions given by equation number 10 to find the value of these two arbitrary constants a and b. So I'm starting with the first one, equation 10a, that f of 0 is 0. In equation number 13, put x equal to 0. We get a times cos 0 plus b times sin 0. So sin 0 is 0. So finally we have f of 0 is capital A, but f of 0 is 0 by equation 10a. So this implies that capital A is 0. So from equation number 13, we can rewrite capital F of x as b times sin px. Now we use the second boundary condition, that capital F of L equal to 0, which is 10b. This implies that b times sin pl equal to 0. Now there are two options, either b is 0 or sin pl equal to 0. If capital B is 0, capital A is already 0. So from equation number 13, we get capital F of x is 0 for all values of x. So this implies that the deflection uxt given by equation number 4, which is the product of capital F into capital G, it is 0 for all values of x and t. So there is no deflection in the string. So this case is also of no interest. So we will explore the second option, that if sine PL is 0. So if sine PL is 0, this implies that PL equal to n times pi. So this implies that P equal to n pi over L, where n is an integer but n is not 0, because P is not 0 and capital L is the length of the string, so it is again non-zero. So finally we have equation number 14, that P is n pi over L. Now we start with equation number 13, and I am setting cap constant b equal to 1. There is no restriction on b can take any arbitrary value, so I am setting b equal to 1. And finally we have infinitely many solutions of that equation number 8. So f of x is given by fnx. I am using subscript n to denote different functions for integral values of n, but n is not equal to 0. So fnx, equation number 15, fnx is equal to sine n pi over L into x, where n is taking only values 1, 2, 3 and so on. So equation number 15 is the solution which satisfies the boundary conditions given by 10. Here very important thing, that I am not considering negative values of n, because we get the same solution except for a minus sign, because sine of minus theta is minus sine theta, and we can combine that negative sign with this arbitrary constant b. Here I am putting this arbitrary constant b equal to 1. If you want to keep this b as it is, you can keep this one. I will discuss the case if we don't remove or don't substitute b equal to 1, then what will happen in the solution. After completing the solution part, I will discuss that with you. So finally we have the solution of first order differential equation corresponding to parameter x, and we have that solution by fnx, which is equal to sine n pi over L x. N is taking values 1, 2, 3 and so on, equation number 15. Now we solve equation number 9 corresponding to the variable t. In case 1 and 2, when k was 0 or positive, we didn't solve equation number 9, because in that one capital F of x was 0 for all values of x. So even if g of t is non-zero, the product of f and g is always 0. So we are solving equation number 9, which is g double dot minus c square kg equal to 0 only for the case when k is minus p square. So equation number 9, we put the value of k is minus p square. So finally we have equation number 9 as g double dot plus p square c square g equal to 0. Now the coefficient of g is p square c square. Let us define a new parameter or a variable lambda n, because p is taking values n pi over L, so I am denoting that by lambda n. So lambda n square is p square c square. Put the value of p, which is n pi over L. I am using here equation number 14 to put the value of p. So finally the equation 9 is given by g double dot plus lambda n whole square g equal to 0. This is a second order differential equation, ordinary one, We can write down its auxiliary equation on the right hand side. It is m square plus lambda n square is 0 and its roots are given by plus minus iota lambda n. So the general solution of this differential equation g double dot plus lambda n square g is given by equation number 16. G of t is bn cos of lambda n t plus bn star sine of lambda n into t, where bn and bn star are arbitrary constants. So using equation number 15 and 16, we have the solution u n x t, because as we change n we get different solutions. So I am denoting a solution corresponding to n is u n x comma t. This is the product of fn and capital G of n. Use equation number 15 and 16, and finally we have equation number 17, bn cos lambda n t plus bn star sine lambda n t. Then we multiply this by sine of n pi over l into x, and n is taking values from 1, 2, 3 up to infinity. These functions are called the eigenfunctions or the characteristic functions, and the values lambda n, that is nc pi upon l, are called the eigenvalues or the characteristic values of the vibrating string. The set of lambda values, lambda 1, lambda 2, is called the spectrum. So this equation number 17, for all values of n, 1, 2, 3, they are the solutions of the one-dimensional wave equation satisfying only the boundary conditions. While finding the solution corresponding to the equation f of x, in this expression, consider the first line here. F of x is bn sine n pi over l into x. We set capital B equal to 1. The reason is, if you want to keep it this one as it is, you can keep it. If we can keep this b as it is, then after calculating the function g and t, as we have in equation number 16, we have u xt function, that is the deflection, is given by the product of f function, capital F, and capital G. Now in capital G function we have two arbitrary constants, bn and bn star, and in this function capital F we have arbitrary constant as b. So we just keep this b as it is. Now we have three arbitrary constants, bn, bn star, and then capital B. See the second equation on this slide. Now this arbitrary constant b, we can take it inside this bracket and we can combine this with bn and bn star. B and bn both are arbitrary constants, so their product is again going to be arbitrary constant. So let's call that as a new arbitrary constant, bn bar. Similarly, the second one, capital B into bn star, this is again going to be arbitrary constant, and we call that one as bn star bar. So from here we can conclude that we can keep b as it is, or we can set capital B equal to 1. We have the same solution. Now last step of the method, solution of the entire problem, and for this one we will use Fourier series. The deflection u subscript n given by equation number 17 satisfies the one-dimensional wave equation given by 1 and the boundary conditions given by 2, that is the string is fixed at the endpoints. But this function will not satisfy the initial conditions given by equation number 3. Now here we use the result that one-dimensional wave equation is linear and homogeneous, and from the fundamental theorem of superposition we have this result that the sum of finitely many solutions un is also a solution of the one-dimensional wave equation. So using this one, we will find out the solution of the entire problem. To obtain a solution that satisfies the initial conditions given by 3, we consider the infinite series that uxt, the deflection in the string, this is equal to summation over unt. I'm taking all the eigenfunctions un and from 1 to infinity. Now use equation number 17, put the value of un function, and we have equation number 18. Now we calculate these arbitrary constants bn and bn star such that the initial conditions are satisfied by the function uxt given by equation number 18. I am rewriting the initial conditions that the initial deflection ux, 0 is f of x and the initial velocity is partial derivative of u with respect to t. This is equal to g of x at time t equal to 0. Now we use equation number 18, equation number 3a and 3b, and we find out bn and bn star. From equation number 18, put t equal to 0. We get ux, 0, and in the summation we have just bn sine of n pi over l into x. On the left side, use equation number 3a because ux, 0, this is the initial deflection and it is given by f of x. So finally we have equation number 19 that f of x is equal to summation over n 1 to infinity bn sine n pi over l into x. Now we have to find out this bn. Now recall half-range expansions from the Fourier series and transforms. In that the function f of x is defined on the interval 0 to l, and for this function we can find its Fourier cosine as well as Fourier sine series because we can extend the function as an even function as well as an odd function. We will use this concept here. Equation number 19. Here the function f of x is defined on the interval 0 to l, and for this function f of x, small f of x, we can find out the Fourier sine series, that is odd periodic expansion of this function. And the formula for the odd periodic expansion is the next line. Small f of x is equal to summation over n 1 to infinity small bn sine n pi over l x, where this coefficient bn, this is the Fourier coefficient and it is given by 2 by l 0 to l f of x sine n pi over l x dx. Now see carefully equation number 19 and the last expression I have marked as star 2. So the star 1 in equation number 19 and star 2. From here we get an idea that we must select these capital Bn, that is star 1, such that it is equal to small bn, that is the Fourier coefficient, because the last expression we have already this expression from the half range expansions. For given function f of x, we can write down its odd periodic expansions where the coefficient bn is given by this formula 2 by l integration from 0 to l f of x sine n pi over l into x. So I am just rewriting the expression from the last slide, the odd periodic expansion of the function f of x. Call this one as equation number 20. Now I am comparing equation number 19 and equation number 20, and just close observation, we must choose these capital Bn's in equation number 19 so that ux, 0 becomes the Fourier sine series of f of x. So thus, using equation number 20, we must select capital Bn such that this is the Fourier sine series coefficient. So Bn is given by equation number 21, that is 2 by L integration from 0 to L f of x sine n pi over Lx dx for all values of n 1, 2, 3 and so on. So finally we have the first coefficient capital Bn. And now start from equation number 18. Differentiate with respect to t. Derivative of u with respect to t is given by equation number 22, which is summation over n 1 to infinity minus capital Bn lambda n sine lambda n t plus capital Bn star lambda n cos of lambda n t multiplied by sine n pi over Lx. Now put t equal to 0 in equation number 22. We get on the left hand side derivative of u with respect to t at time t equal to 0, and on the right hand side we just get capital Bn star lambda n sine of n pi over L into x. Now we use the initial condition, that is the initial velocity at time t equal to 0 is gx. So finally we have equation number 23, that gx is equal to summation over n 1 to infinity Bn star capital Bn lambda n sine n pi over L into x. Now we must choose these capital Bn stars such that equation number 23 is satisfied. We have to find out Bi's like this. Now this function g is again defined from 0 to L. Here we again use the Fourier series, that is half range expansion, and now we say that we must choose these capital Bn stars so that at a time t equal to 0 the derivative of u with respect to t becomes Fourier sine series of g of x. So thus Bn star lambda n, the expression with sine n pi over L into x. In equation number 23, I am just excluding the sine function. Whatever is the coefficient there, I am just picking that one, which is capital Bn star lambda n. This is equal to the Fourier coefficient in the sine series, which is 2 by L 0 to L g of x sine n pi over Lx dx. So the capital Bn star is given by equation number 24. Here I am putting the value of lambda n, which is n c pi upon L. Take it on the right hand side, simplify this. Finally we have capital Bn star as 2 upon n c pi integration 0 to L g of x sine n pi over Lx dx, equation number 24. So equation number 18 along with equation number 23 and 24 with capital Bn and capital Bn star is the complete solution of a one-dimensional wave equation given by partial differential equation 1, boundary conditions given by 2 and initial conditions given by 3. Now discussion about the eigenfunctions. The eigenfunction u with subscript n is given by Bn cos lambda n t plus Bn star sine lambda n t sine of n pi over Lx given by star. This represents a harmonic motion having frequency given by lambda n upon 2 pi cycles per unit time. This motion is called the nth normal mode of the string. The first normal mode is known as the fundamental mode and the others are known as overtones. Now we talk about nodes where the deflection in the string is 0. So this is sine n pi over Lx is 0. and this is 0 when x is L over n, 2L over n, and similarly last is n minus 1 divided by n into capital N. The nth normal mode has n minus 1 nodes, that is the points of the string that do not move. So if n is 1, we don't have any node. For n equal to 1, we have 1 node. For n equal to 3, we have 2 nodes, and similarly we can move further. I will discuss numerical problems and some special conditions on this function, and we simplify this solution of one-dimensional wave equation further in the coming lecture.